Okay, so let's look at different types of heterojunctions. Again, this is in the context of the bipolar junction transistor, and I had shown you the chart here that relates lattice constants A to band gaps delta or EG. And so you have a toolbox of different materials. What's not in this chart is the electron affinity or the electron vacuum level for these semiconductors. So that's, in a sense, a third axis that is playing an important role in the next section. Okay, so I had already shown you a type 1 heterojunction. It looks like this. For example, you have N-type AlGaAs and P-type gallium arsenide. All right. The band gap here on the left, the AlGaAs is at 1.8, and the band gap for the gallium arsenide is 1.42. Those are typical values in a system like this, okay? Now, what you have is a device that likes to accumulate some electrons at this interface. And here's a reminder. So electrons live above the conduction band, right? And the Fermi level kind of marks the sea of electrons. And at higher temperatures, you have sort of a bubbly sea, and the electrons can be thermally excited. At T equals 0, you would have an absolutely flat Fermi function and a flat Fermi sea, so to speak. So what you have here is there is a sea of electrons sitting in this triangular notch. And because the Fermi level is pretty close to this triangular notch here, so there's thermal excitation that keeps the electrons there through a variety of processes. We haven't talked about how these electrons get there, but they, in thermal equilibrium, they will be there. So that's an accumulation layer. Okay? On the left-hand side of the junction, for the holes and for the electrons, really, so this is an NPN, right? So for the electrons, the Fermi level is pretty far away from the conduction band edge, right? So you will have the normal N-type sea of electrons here, but other than that, you don't have a charge accumulation on the left-hand side. You really have a charge depletion on the left-hand side, okay? So in this kind of junction, you have an accumulation in one direction and a depletion typically in the other direction. Okay. Now, let me take the same hetero structure. So we keep the same 1.8 aluminum gallium arsenide here and the same gallium arsenide here, but let us dope it exactly opposite. So where you have P doping here and N doping on the right. So it's flipped from what we had before, right? The material is the same, but now we basically flipped the doping type. And the heterostructure looks quite different because the band bending on this heterostructure is very different. You do have a heterostructure offset here, but these under this condition, the Fermi level is very far away, it's quasi mid-gap away from the conduction and the valence band. That means there aren't a whole lot of electrons there. This is a heterostructure where you will have depletion of both electrons and holes. Okay? And again, keep in mind, it's still AlGaAs here and gas here. But the band structure looks very different from left and right, okay? Very different, just by the doping and the relative differences of delta, EG, affinity, etc. We still satisfy the same equation that we had up here, but the band structure ends up looking very different because the built-in potential is very different, okay? All right, let's compare these two again. So you have accumulation here, for the electrons, and depletion here, not many electrons at all, and this one has depletion and depletion at the interface. Okay? All right, let's look at another junction type. This is called a type 2, and here I'm choosing the indium aluminum arsenide indium phosphide junction. Okay, so again we start from drawing the Fermi level flat, then we draw the we have the valence band on the right, so we are p-doped on the right, and have the indium phosphide there, and draw the conduction and the valence band. We draw the vacuum level, and we do the same thing on the left-hand side, and here it's the indium aluminum arsenide, and draw it like this. So same procedure as before, but now you see that the electron affinity, or the vacuum level for the electrons here, is very different in these two materials, okay? So remember we looked at the chart here, this is indium aluminum arsenide, and this is indium phosphide, okay? So these are quite different materials. They have the same lattice constant, and you can grow them on top of each other, but the electron affinity is quite different. So let's see what kind of band structure emerges. So again, we're connecting the vacuum level and transfer the conduction and the valence band down. And let's do this on the N side, and now on the P side. You can see a quite different heterostructure, okay? Now this heterostructure is very interesting in that now you have a heterostructure, or a triangular notch, on both sides of the junction, okay? And so you can have accumulation for the electrons on this side, right? So you can pile up electrons here, and you can also pile up holes on this side, okay? So let me go back. You can pile up electrons here, and under this bias condition, this Fermi level is far away from this edge, but you can imagine a bias condition where you can start to pile up holes here, okay? So depending on the bias condition, you might be able to get accumulation on either side of the junction, okay? All right, so this is type 1 and type 2 junctions. They look quite different. You can already begin to appreciate you have really a toolbox of different materials, of different heterostructures you can assemble. Here's another one that's much simpler in a way. And here we're not changing P and N doping, but we keep it both N-type, but we build a junction out of AlGaAs and GaAs. So gallium arsenide on the right, aluminum gallium arsenide on the left, and keep a slightly different doping. And what you see is you have a notch that is building in the conduction band. So this is a junction that is an isotype heterojunction, meaning it has the same kind of carriers we're interested in by our choice of doping, but you can have pretty strong accumulation in this layer here. And this is a typical heterostructure where you might want to transport electrons, if you will, vertically in this channel here, where you induce carriers, and this is a high mobility transistor that you can build out of this, okay? So this transistor might have naturally, or this structure might have naturally a lot of electrons available for you in that triangular notch. Okay, and out here you have a depletion region where there's really no holes or electrons on the other side of the structure. Okay, now side note, what you have here is a heterostructure that looks a little bit like metal-metal junctions, where you can build thermoelectric coolers, etc., where electrons from one side to the device traveling to the other might lose or gain energy depending on which way they travel, and therefore you can have cooling or heating in a junction like this. So you build thermoelectric coolers this way with metal junctions, and you would explain the metal junction in the same way as you would explain the transport across these heterostructures here. All right, now we're getting to a type 3 heterostructure. Now, this one looks quite interesting, and I'm starting from a slightly different point of view. I'm not starting from the Fermi level being flat throughout. I'm imagining that I have these two materials far apart from each other, and I want to show you the dramatic difference in these materials. The band gaps, ballpark, are the same. Well, they're not quite the same. This is 0.36 on the right-hand side. That's indium arsenide. Very small band gap. And a band gap for gallium and antimonide that I haven't talked about before. And the band gap is roughly double. The electron affinity of these materials is very different. So the value of Chi1 on the right here for indium arsenide is much, much larger than the Chi2 of the gallium antimonide. All right, so let's see what happens when you line up the Fermi levels and stretch out the potentials. So you get a huge built-in potential, and that translates with the band bending into the conduction and valence bands to be looking really interesting. So look at this. You have a huge offset in the conduction band, like this. And let's zoom in a little bit more here on this. And again, as a reminder, the electrons would like to float above the Fermi sea. And I color-coded the conduction band in blue now. And the electrons would like to sit here, right? So and if you were at 0 temperature, they would fill up all the states up to the Fermi level. And if you look on the left, the holes would like to float up, right? And they float at the top of the valence band, and you'd have a sea of holes like this. So what you have now are two sheet charges of electrons and holes that are very close to each other. So this is a pretty cool heterostructure that is being investigated for all kinds of interesting device features. And this is called a type 3 heterostructure, where you have an accumulation layer like this on either side of the junction, and it compares like this to the other types that we had. So here is type 3 accumulation on the left and the right. Then we had a type 2 where we had an accumulation on one side and depletion on the other. We can have a type 1 that has depletion on both sides. And then I had talked about a type 2 that in this configuration has accumulation on the right and depletion on the left, but you might, through a bias, achieve a depletion accumulation in the opposite direction. So this is your toolbox of different heterostructures that you can play with as you design transistors. Playing with that is called band structure engineering. You engineer a new landscape for the electrons to travel in. So that's a field of research and a field of practice. And you'll see at the very end of this HBT lecture series here examples of how complicated of a transistor people create in this kind of world of different heterostructures. All right. So the summary is we have a toolbox of these different materials. We have a toolbox of different types of heterostructures we can come up with. The HBT, I'll show you, will be a solution to the limitations that we had found to the normal BJT. And the equilibrium solutions for these band edge diagrams are very, very similar to what we had done for the BJT. There's no new methodology. The only thing that's different is, Chi1 and Chi2 are different values, and the dielectric constants are different values, but the rest of the methodology that we have used carries through just as well. And depending on the alignment, there could be different types of heterojunctions. Each has different usage. So that's sort of a general overview of heterostructures as such and what's available out there. So next, we will be talking about specific types of junctions for the HBT, and we'll start out with the abrupt junction, and I'll see you in the next section.